Hello, everybody on the other side of the Zoom. Okay, everybody, this side is taking bathroom break. So if you want to go, then I will rewind a little bit and talk about the, sorry, not so important stuff, but can be a little bit more fun. Hello? Okay, can you hear me now? All right. So I think we can resume the Monday morning talk. Okay, so here we go, right? I was telling everybody that Charles Lindbergh, actually, he was an experienced pilot, but he was also can be viewed as a aerospace engineer, knows about the airplane. So this is the airplane he asked the Ryan Airplane Corporation to design by thinking everything in the reversed manner, right? Think out of box, so-called. Okay. First thing he said is he's going to fly by my hips himself, no co-pilot, no navigator, because no navigation. His reasoning is he's flying toward the east. Okay, and he knew his airplane will be drifted one way or another, but he knew European continent is big enough, so if he kept flying, he should be able to hit somewhere between France, Spain, and Norway. So that's why. Once hit the coast, he just need to follow the coastline to reach the Paris. So that's why he said he didn't need the navigator. Okay, radio operator, again, radio operator, at the time was only used for the case for emergency. Emergency happens. If that happens, then he knew he was dying. So he said, I don't need the radio operator neither. Okay, so because of those things, he were able to keep the cockpit very small, compact for himself only. And because of that, airplane became very small. Because of that, he just needed a small engine. Small engine required smaller fuel tank. Everything became smaller. Good. That was the, right now, for us, it seems a very reasonable thought process, but at that time, that required significant out-of-box thinking. Okay. Now here, as you can see, there is no front glass windshield is not there. That means taking off, landing, he cannot see the front. Okay. But good news is at the time, airfield is not like today. Today, you can see the airstrip, right? Runway, clearly defined runway. At the time, airfield is like a huge soccer field. You can take off any direction, land at any direction, as long as you can adjust the direction of the airplane to the proper location, you can take off, you can land. That means you don't need the front windshield or glass, okay? Besides, if you have front windshield, it will sort of stick up. That will cause more friction. Removing that one, you can make this space portion very smooth. Less friction, less fuel. That's second part, okay? So that's why, again, he was bold that way. And finally, the last part was he requested the Lion Airplane Corporation engineers to make the vertical stabilizer. This is called the vertical stabilizer. Stabilizer means to stabilize the airplane, right? Okay, stable airplane is usually ideal, but he said, let's make it very small. That means make this airplane a lot less stable. Okay, and that also surprised the engineers. They said that's very dangerous. You're flying almost 40 hours. You don't want the airplane to be unstable. He said, I'm flying by myself. Nobody will wake me up. Okay, if I have a very stable airplane, I will fall asleep. On the other hand, if I have an airplane that is very unstable because of the small stabilizer, that will keep me awake. Reverse thinking. So let's do it. And he finished it. He was successful and he completed his dream. Okay, so I think, sorry for sidetracking, but this is one of the great story about the great engineer who can think out of box. Okay, yeah, all great inventions are done out of box thought process. Okay, all right, sorry for sidetracking. Okay, All right. So let's go back to the not so exciting strains. Okay, we talked about the normal strains. Okay, here's the example you have seen in your strengths of material class already, so I'm not going to repeat this. Okay, then I'm going to talk about the shear strain. Okay, small review of the mass. Okay, let's say we have a y and x. Clearly, this is a linear function. All right, so what is the alpha here? What is alpha? Beta? What do you call this? What is alpha? Oh, let's see. Somebody's answered on the. Okay. Does anybody know what is the what do you call this alpha and beta? Alpha is shady. Yes, slope. Yeah. And this is intercept, right? Okay, good. All right. So alpha is called slope. Okay. Alpha is slope. Beta is intercept. Okay, good. So slope. Okay, slope is a keyword. Slope. Okay. All right. Okay, and slope can be also, if we draw a tiny triangle here, assume this length is dx, dy, okay, we can say also slope can be expressed this way, right? Good. Okay, and also by looking at the triangle, this triangle, okay, dy dx is equal to tangent theta, okay, so we can view that way too. Good. All of them are talking about same slope. Okay. All right. So idea is the reasoning I'm showing this is basically if you have a function y to find out the slope, you just need to differentiate it by x or time or whatever. Okay. All right. So here we go. Shear strain. The idea of the shear strain is if you have a small element that has the square shape, apply the shear stress, then you will force this shape into parallelogram like this, right? This end is going to displace this much. This end is going to displace this much, okay? All right. And because of that, this line will be tilted. This line will be tilted. There will be an angle here, okay? So these two angles combined is called, angle change is called strain. Good. Okay. Sometimes we will combine two angles, treat this as one number and divided by 2 and call that one as average shear strain too. Basically, shear strain is the angle change from square to parallelogram. Okay. All right. Okay. And as you can see, we have partial differential equations here, but you can, each party can view that as a pure differential equations. That is the slope, right, times dx, okay, will give us the displacement here, okay. All right. And here, of course, this picture is exaggerated. Usually it will not tilt that much, just a little bit, small strain, okay, that means angle change is very small. Then we can say tangent alpha can be viewed as sine of alpha over cosine of alpha. Angle is very small. That means this cosine is almost 1. Sine of alpha is almost alpha. So tangent alpha can be viewed as alpha. So that's why this is equal to alpha. That's the way we engineer try to simplify the problem. Okay. All right. But anyway, takeaway message is basically shear strain is the angle change from square to parallelogram. Okay. All right. Okay. So here's the another boring example. Okay. Displacement in x direction is defined as k times y. Okay. Clearly the function of y direction. Okay. Displacement in y direction says all of them are 0. That means height will never change. Indeed, when you apply a shear deformation to a square, usually it would twist a little bit, just twist a little bit, okay? Become a slight parallelogram. And because of that, we can almost assume the height will never come down. This is rigorously speaking, it's not true, right? If you twist it enough, this height will come down, right? This will be sloped this way, the height will come down all the way here. But when we're discussing this kind of problem in small strain framework, we can say this line will never come down much. So height will never change, okay? Thickness will never change, okay? So using this displacement field, again, right? We apply this differential equation to here, then we can find out the shear strength of this rectangle twisted into parallelogram is K. Good, all right? Okay. All right, now we talk about the stress and the strain. Now, finally, we can talk about the stress-strain relationship. And once plot that one, we can say, we can find out the stiffness of the material. Okay. All right, why we need to know the stiffness or compliance? Reverse of the stiffness, softness is the compliance. Okay. All right, so what does stiffness means? If you apply a same amount of force to sample A and B, okay, same size, okay, then if the material A or object A stretches more than B, same amount of force to A and B, okay, A and B, if A stretches more than B, then you can say that means B stretches less, then B is stiffer than A, right? Okay, right? That's the way usually most people would describe material stiffness. This is correct. Or reverse it, okay? If we apply same amount of stretch to A and B, okay, and same amount of stretch, then B requires more force to achieve same stretch, okay, then B is stiffer, correct too. Okay, that's the way usual people would describe something is stiffer or softer, okay? But we are engineer and we know, now we know the stress and the strain, then we can come up with a little bit more scientific way to measure it, okay? All right, what we do is usually create the so-called doggy bone sample. It looks like a dog bone, right? Okay, and many people call this as a doggy bone sample too, okay? And create it, okay, so that tester can grab both ends firmly, okay? Put in here, apply the force to measure the, this will measure the how much force is applied. The strain has to be measured. Usually we will glue the strain gauge, okay, onto the center, okay? Then we can measure the strain, right? Then with those two, oh, here you go. I created a video yesterday, right? Good. All right, so the video of this purpose was, okay, one thing, if you stretch more, clearly the sample will get narrower, right? Basically, volume cannot change, okay? So it will get narrower. That's one thing we should notice. And the other thing is, okay, the force, apply the force and apply the change of the length, in this case, can be viewed as time function, but it's exactly same. When I let go the force, length go back to the original length. So there is no time shift between force and the length or change of the length, okay? All right. So takeaway message is in this elastic problem, apply the force and deformation, there is no time dependency in between, okay? So because of that, we can plot this kind of stress-strain relationship, okay? Stress is given by force divided by cross-sectional area. Usually we will assume the cross-sectional area from here, same all the way, okay? Because of that, since we're assuming the cross-sectional area same throughout, so up until here, we will get the reasonable stress-strain relationship. After that, it will start curve up, plateau, and come down. Actually, this is kind of weird response because this weird curve is caused by the assumption of cross section is uniform. Okay, cross section actually shrinks more and more and more. Okay, but when we are drawing this kind of plot, as you remember from strength of material, we assumed cross section is uniform. That's why we get this kind of weird curve. Okay, all right. Okay, and this part is linear, elastic, right? Elastic, that means if I stop applying the force, let go, then the material will shrink down, follow this curve and go back to here, right? Good. But if you keep applying it, the stress, then you will hit the yield stress. Then after that, you get the yielding, permanent deformation. Then after that will be plastic too. Okay. Actually, this part is already plastic. Okay. All right. But the whole purpose of doing is usually we would like to look at this part. Okay. All right. Unless you're interested in failure analysis or something, most of us are only focusing on this part. Why? By looking at this slope shows the stiffness, right? Stiffness of the material, correct? Right? Okay, if we do the same thing to different material, if the slope is a lot less steep, then what does that mean? Softer, correct. If this is steeper, harder or stiffer material, right? Okay, so that's it. We do this because most of the time we are only focusing on this linear part, this slope that is called the stiffness. Good? Okay, by comparing the stiffness, you can tell the material is stiff or soft. Okay, all right. Okay. All right, so again, here, if you can measure the real-time cross-sectional area at each strain, at each step, you can measure cross-sectional area. The true stress relationship will keep going up and up and up like this. Okay, and actually rubber or polymer shows this kind of pattern too. The rubber, if you pull the rubber, but this part is very small. And after that is the long non-linear curve through and through and through all the way to 100%, 20%. Okay. Most of us think this will never happen to elastic rubber. Actually, it does. At the very beginning, it shows something like this. But after that, we will have a long non-linear curve for polymer or non-linear rubber. Okay. All right. Okay, and different material has a different response too. Okay, most of the ductile material like stainless steel will show this kind of stress-strain relationship. Okay, and most useful part is this elastic part. Yes. However, if you're thinking about when the material will fail, actually this failure strength is very important too. So if the failure stress is very important, using ductile material, stainless steel is very important. Good. Brittle material is very hard. It's very hard, but it's go and snap. Okay. All right. The funny thing is in biomedical engineering, orthopedics, okay, the screws, orthopedic screws, we use brittle titanium. Okay. All right. Because the idea is titanium is stiffer than stainless steel, correct? But the problem is when we create the screw using titanium put into a bone, okay? The screw is sitting there 10 years, 20 years, deformed a little bit every day, then it snaps, okay? All right. So actually, in my view, orthopedic screws should be using the stainless steel. Okay, but it is too cheap. So that's why in US, medical company promote the titanium screws to make more money. Yeah. All right. Anyway, the slope is the C. Okay. All right. A couple of the terminologies. Okay. All right. Stiffness or Young's modulus is the slope part of this linear stress-strain relationship. Okay, if we measure the area under this curve, usually area means the how much energy is stored in the object through that process. So this area is bigger, that means more energy can be absorbed by that object. Okay, so that is the elastic strain energy. Of course, bigger is better. If you have a steeper object, triangle is bigger, so area is bigger. Yes. Okay. If you were considering about the failure of the object, then you would like to measure the modulus of toughness. That comes from measuring the stress-strain relationship entire process. Okay. Then measure the entire area. This will be much bigger than this, but that means this material can absorb this much energy, much more tougher. All right. Okay. All right. Poisson's ratio. Okay. All right. Poisson's ratio is basically when the object is going to stretch or compress, the width will change, right? In this case, it's showing rubber cylinder is compressed. Clearly, the cylinder width is getting fatter. All right. The ratio between the axial strain and the lateral strain is called Poisson's ratio. Okay. All right. Then Poisson's ratio is given by minus of strain lateral direction divided by strain in axial direction or longitudinal direction. Okay. Why there is a minus? Okay. If you have a tension testing, this is positive. If you have a tension, this will shrink. That means this is what? Negative, right? Then if we leave it as is, negative minus positive will be negative. Looks not so nice, so we'll put the minus here. Then it will become always positive. If you have a problem like this, longitudinal strain is contracting, so this is negative, but this is becoming bigger, so this is positive minus negative. Again, it's a negative number. To rectify it, to add the minus, you have a positive. That's why. So Poisson's ratio is always positive. Okay. All right. Hey. What was, oh, okay. Now this slide, I'm going to talk about the Poisson's ratio, what's possible. Okay. A couple slides back, I said, if you put this test sample, put the test sample onto the stretch test, okay, you can find out the volume change between before and after and before. Volume ratio by ignoring the higher order term can be given this way, okay, all right. Then, if you have the material that is pretty much no volume change, okay, water does not change the volume. If you put the water in the plastic bag, you can pour, compress it, volume never changes. Rubber, polymer is pretty much the same way. Rigorously speaking, it changes a little bit, but macroscopic point perspective, volume is same, okay? All right. So volume is same for, macroscopic way of analysis tells us polymer or rubber, volume never changes. That means this term has to be 1, right? Good. And also in this case, EXX, EYY has to be same. This has to be same, right? Okay. Then in that case, we can say the ratio between the EZZ, that's the longitudinal strain, EXX is lateral strain, okay? Converting from here to here, this and this is assumed to be same, then we can find out this is equal to 1/2. Good. So if you have a polymer or rubber, do this kind of testing, Poisson's ratio, or actually biological tissue, same way. If we cut our brain tumor, okay, ligament tendons, I know you don't trust me, but you can come to my laboratory later. I can cut your tendon out and do the testing. Then I can show you Poisson's ratio is 1/2. Good? Okay. All right. So that's a special thing about the polymer in rubber and and biological tissues. Okay, and non-shrink case, actually, I myself never encountered, but theoretically that happens too. Okay, elongates, never shrinks. Okay, all right. If you have a doll, maybe bread doll, maybe, I don't know. Okay, so this is another extreme case, never shrinks. Okay, all right. So if that's the case, no shrinkage, so EXX, EYY is 0. Okay, in this case, it should be equal to 0. Okay, so the Poissons ratio, theoretically speaking, upper end is this, lower end is this. Most of the steel is like 0.3-ish, right? Okay, and 42, good, all right. Okay, example problem, we can skip it. All right. Okay, the previous slide was talking about the tension testing, right? Then next question is, how can we measure the stress-strain relationship for shear deformation? Okay, the easiest way is create a doggy bone shape like this. Okay, here is cylinder, here will be a usually hexagon shape, and put it into a gripper and rotate. Okay, rotate. Okay, gradually rotate. To rotate, you apply moment or torque. Okay, and you can see one end is going to twist more and more and more. Okay, if this end is fixed. Okay, but action torque, reaction torque. Okay, even this end is fixed, there's a torque here. Okay, all right, then rotate, rotate. This is going to rotate, rotate, rotate. Remember, the shear is the angle change. Good. So using this kind of simple tester, you can evaluate the shear strain by this total length, radius of the cylinder, angle. Okay, shear strain, average shear strain is given by this. This J is called polar moment of inertia, given by this. Okay, all right. So radius, before testing it, you can measure the length R. Oh, sorry, L, radius R. So this J, polar moment of inertia, when you do the testing, is calculated. Radius is known, length is known. Okay, torque, we will apply it, so T is known, right? Okay, and we know, okay, for the linear part, Hooke's law also applies, shear stress, shear strain. Okay, in between G is called shear modulus. Combined together, oops, there's this. Okay, we'll get this relationship. Okay, so this is going to, we can measure, right? T is recorded. L, we already measured before you do the testing. J is given by radius. This is already measured before testing. So what we can say is blue parameter L and J is already measured, calculated, or what did I say? Okay, this is already known. Okay, green parameter is measured through the testing. Okay, so these parameters combined, you can find out the G, shear modulus. Good. All right, we're all doing this because we would like to know the modulus, shear modulus or Young's modulus. Then you can compare, this is harder, softer. That's why. Okay. All right. And that is why. Okay. All right. So again, doing that kind of testing, we can get the similar shear stress, shear strain relationship like this for ductile material. Okay. And linear part, this usually it's very small. Linear part of this slope, the slope of this linear part of the curve is called shear modulus G. Okay. All right. Shear strain, angle change, shear stress is the twisting stress. In between is G, shear modulus. And shear modulus and Young's modulus E. Young's modulus is the stiffness measured from the stretch test. Good. Okay. This is Poisson's ratio. So if you have a homogeneous material, rigorously speaking, not many materials are homogeneous, but most of the time we assume stainless as a homogeneous, tofu as a homogeneous. Okay, definitely I think the tofu is a homogeneous, isn't it? It's very silky. Yeah. Yeah, can be this relationship holds. Good. All right. Okay. Okay. So if you have a 3D case, okay, 3D object, how can we measure all those information? Okay. It's not so relevant. 3D information, if you want to find out the Young's modulus, Poissons ratio, all those things for the 3D object, in the reality, all the materials are can be subjected to 3D stresses, right? So if you want to find out all parameters in the 3D space, what should we do? Okay. Fortunately, we don't need to apply 3D forces onto the object. We just need to do the simple 1D testing each time. Okay. 1D testing, applying stress in X direction. This holds, okay, stretch this way, shrinks in X and Y and Z direction, Poissons ratio kicks in, okay? Repeat the same thing for Y direction, Z direction, right? Then you basically corrected most of the information, okay? Then to set up the 3D, first thing we are going to do is set up the 3D stress-strain relationship or strain-stress relationship this way, compliance relationship, okay? Because stiffness is down here, so it's a compliance. 1 over E is a softness or compliance, okay? Combining these equations here, okay? All right, we can repeat the same thing for these equations. Shear is actually very simple, okay? Shear is simply applying the shear on each directions. You can set up this because shear has nothing to do with actual stresses for homogeneous case. So this can be done easily. This is an independent shear test, shear test, shear test. Then finally, we can get A, B, C, D, E, F, G, 6 equations. Okay. All right. Oh, sorry. 1, 2, 3, 3 equations. And here, 4, 5, 6. Okay. Usually we would like to have an equation of stress on the other side, strain on the other side. So combining 1, 2, 3, 4, 5, 6, struggle a little bit, then you can find out these relationship. Okay, so this is the 3D stress strain relationship. Good. And this is for homogeneous case. So the parameter is Young's modulus, right? Stiffness for stretch test, Poissons ratio, and shear modulus. Good. All right. Okay, I think then we can go to our lunch, I think. Come back in the 1 p.m. 1 p.m. and I will rush through everything else here. Okay, thank you so much. See you in the afternoon.